So we will learn a little bit about how the Apache Arrow project is changing pandas and Dask for the better, hopefully. The introduction about me, we can keep this brief. Tamara already mentioned all the important things. I work at Coiled, where we deploy Dask for our customers. And my main responsibility is improving Dask and pandas. So that's nice to be able to work on open source almost full time. This talk will interleave a little bit pandas and Dask. Pandas, I guess almost all of you will know what it is. It's a Python data analysis library that's used all over the world, but it's a mostly single core. So as soon as you want to scale to huge data sets, pandas won't be the best tool for the job. And that's where Dask, but more specifically, Dask data frames come in. Dask at its core is a general purpose library for parallelized and distributed computing in Python. And one of its strengths is that it integrates with all the PyData libraries. Among those, pandas, Dask, scikit-learn, XGBoost, Optuna. Like most of the PyData libraries have some kind of Dask integration. Today, we will focus mostly on Dask data frames, which is the pandas integration. We will talk about a bunch of different things. Pandas started moving more towards Apache Arrow for certain parts of the API a couple of years ago. And this resulted in a number of features that are very helpful for like usability, performance, and memory consumption. Users can now create Arrow-backed data frames. That means that the data frame is completely backed by Apache Arrow instead of NumPy. Or use Arrow strings, which is for pandas the biggest strength of Arrow at the moment. They are just way more efficient than what pandas used in the past to represent string colors. Then we have copy and write. This is a new feature that will be enabled by default relatively early next year. Dask built a new shuffle algorithm, which is used to send data over the network. That is heavily based on Apache Arrow. And we are currently, that's my main responsibility at the moment, building a query optimizer for Dask data frames so that it can make your queries more efficient for you. We will start with a quick demo, just to get an impression how Dask behaved like 8 to 9 months ago. I'm running a query here that's heavily merge-based. Merges are very expensive in a distributed system. And it also does a bunch of group bys. These are both things that Dask historically wasn't very good at. And we will now see why. On the right, you can see the Dask dashboard. In the top right, this is what Dask is currently executing for us. For those of you who don't know Dask, white and red is a sign that something's seriously wrong with your workflow. As you can see, we have a lot of white, a lot of red here. And we have many, many small dots. These are also a sign that your workflow isn't structured properly. And this is just going on until the workflow finishes. And it uses significantly more time than what would be necessary if the backend implementation would be more successful. The talk is structured in a way that we will go through a bunch of features that pandas and Dask added that will help improve this workflow, and then we will see an end-to-end comparison right at the end that will show side by side how much faster Dask got since these settings were active earlier this year. I won't wait till we are finished here, otherwise I'll run out of time in the end. It's that slow. So we will mostly talk about strings, missing values in the first chapter, strings and missing values. The earliest feature that came to pandas that was backed by Apache Arrow is an efficient string data type implementation. I guess most of you who have data frames that are a little bit bigger than tiny have noticed this, that the pandas default string data type isn't very efficient. So this brought us huge improvements. But also we gained access to a huge number of different data types. Previously, everything that was like non-numeric or bool basically fell back to NumPy object. And now we get access to stuff like bytes, decimals, structs, list data types, and like many, many more. As you can see, the left side is like the default NumPy backend. You can see everything's object. Although it looks the same on the top, the right is with arrow backing, and what we can see here is that every one of these columns has a specific data type representation, and not everything is stored into like object. This is very helpful for performance and general usability of these data types if you want to have anything that's like non-numeric or non-bool. And like one of the biggest advantages of Arrow from a user point of view, if you want to do different things with different libraries, is that the interoperability is great. You can switch zero copy from pandas to Spark to Polars to DuckDB. All these libraries out there that are somehow using the Arrow memory format. I've talked a little bit about strings already. The big discrepancy between NumPy object and PyArrow-backed strings is one of the reasons why we will start inferring strings as PyArrow-backed by default in Pandas 3.0. Pandas 3.0 is will hopefully be released like in Q2 2024, so it's not too far away. This means that you would typically have like something like a data frame with string columns would be inferred as object, which is very memory intense and not very fast. And you don't have to change anything. We will basically just flip a switch, and then we will infer all of those as PyArrow-backed. This string data type is modeled after NumPy object, so the behavior should be pretty similar to what you are used to with object data type. But the memory footprint will be significantly lower, and it will hopefully also be a lot faster. But more important is the memory savings if you have bigger data frames. You can easily try this out today. If you are on a Pandas version that's 2.1 or greater, we added a new option, PD options future infer string. If you set this to true, then you will get the behavior that will be the default in Pandas 3.0 like today. If you just set this line top of your program, script, whatever. This also means that we don't have to convert to object if you read Parquet files, for example, that are already backed by the Arrow memory model, which is roughly 75 to 80% of the runtime if you read in a Parquet file with string columns at the moment. The conversion, not the actual reading. Dask made this jump a little bit sooner. PyArrow-backed strings are already the default in Dask. And like it's a little bit easier to profile stuff with Dask because if you have hundreds of gigabytes of data on your cluster or on your huge machine, then computations will run a bit longer and you can like look at what's going on there. What we've seen is that it's roughly 2 to 3 times faster for most stuff compared to NumPy object. But for most Dask users, performance isn't that important. Stability is significantly more important to them than actual runtime. And what Arrow strings help there by a lot, since they reduce the memory usage by a drastic amount. This graph here is like object data type had like 220 gigabytes, PyArrow strings close to 100 gigabytes. So it's more than a 50% reduction, but the important thing is this data set only had 3 string columns and 17 columns with numeric or categorical data types. So switching 3 columns from object data type to PyArrow-backed strings reduced the memory already by 50%. If you have like 20 string columns, then this factor will be significantly bigger than our small 50% here. It's on since July in Dask. As I said, it's already on by default. So if you install a new Dask version, then you will just get this behavior out of the box. The next part of the talk will be about copy and write. Copy and write is a feature that will also be enabled by default in Pandas 3.0. And I like to call it more in the sense of getting rid of the setting of copy warning. This brought us a lot of pain over the last, I think 8 years now. And I am hopeful that no user will actually miss it. Like I asked around and I couldn't find anyone who actually liked it. Maybe I didn't look hard enough, but I don't think so. So I guess most pandas users will know this. You have a data frame, then you filter this for a subset of your rows, and then you update the subset with log or ilog, just modifying the data frame in place. And then you get this nice warning, setting with copy warning, which basically means that data frame will not be updated, only subset. But I don't think that most people care about this. So it's just very noisy. It's a false positive. It really doesn't matter. So this created a lot of confusion. The setting with copy warning doc page is actually one of the most visited doc pages of the pandas docs, which was concerning. That's why we implemented copy and write mostly. Copy and write is a relatively simple idea. It won't ever be possible to update two pandas data frames at once with one operation. So in our previous example, copy and write will guarantee that always subset gets updated only every time, no matter how you create it. This here triggered a copy, but you could also create subset through view mechanics, and then it would update both at once. All of this will be gone. So there will never be a confusion if your operation updated 1 or 2 or 5 data frames, which provides a simpler and more consistent UX. This is at least what we are hoping for. So every operation only updates the object you are currently operating on. So you don't have to keep in mind that there might be another data frame like 10 lines above your current line of code that might get modified. This will just never happen. There's no confusion anymore about copies and views. Everything behaves as a copy. And so we can get rid of the setting for copy warning. I am really looking forward to that PR that rips that up. And then there's a third thing that is probably the most important thing for users, I guess. Pandas utilizes defensive copying very, very heavily across the API. And all of this will no longer be necessary because there's no view anymore that you could modify. So we can just get rid of all these defensive copies. We did a bit of a fake benchmark here. All of these methods, like rename, assign, drop, type, reset index, set index, all of them perform a defensive copy at the moment. And we, as I said, can rip that out with copy and write. So without copy and write, the runtime is 2.5 seconds. The data frame has 3 million rows, so not too big, but also not very small. And with copy and write, we get this runtime down to 13.7 milliseconds. So roughly an improvement of factor 200. Obviously, this won't be true for the average pandas workflow. As soon as you do a group by or a merge, then copy and write won't be helpful anymore because data most likely will need to be copied anyway. But as long as you're doing reshaping operations that don't change the length of your data frame, you will see a huge performance improvement. And then if you go back to group by, you will be back to normal, how it behaves right now. This is also something that you can enable right now. We basically finished the implementation in Pandas 2.1. So it's more or less in the state that we will release it by default in 3.0. So there are no known hidden bugs. No known bugs left anymore to address, at least as far as we know. There might be something that we missed. That's the Panda part. Now we will look a little bit into how we made Dask data frames multiple orders of magnitude faster. The theme of this part will be Dask data frame is fast now. And the things that contributed mostly to this, except arrow strings, what we've already seen, is a new shuffle algorithm and a query optimization for Dask data frames. The latter part is not on by default yet, but we will see how you can enable this if you want to in a little bit. Dask historically struggled badly, basically, with shuffling. It strained the scheduler, it didn't utilize the cluster very well, it copied a lot of data from one machine to another, which is very expensive in a distributed setting. Doing something that can operate on one machine actually doesn't matter performance-wise as soon as you need shuffling at some point in your workflow. So this was improved earlier this year, and we are still actively working on improving it further, but the performance increase and stability increase is already huge. We implemented a new shuffle method that's called P2P shuffle. The two most important features are like better performance and less strain on the scheduler. Previously, the number of tasks, which is what Dask executes, grew exponentially based on the size of your data. And now it just grows linearly with the size of your data, which is a really, really huge improvement for how Dask operates in the backend. This is like a Dask dashboard, as we've seen a little bit briefly earlier. On the left-hand side, we see a task-based shuffle. We can see this is the memory usage. Blue is good, orange is not great, and gray is very bad. We can see that this is like heavily straining memory usage. As I said earlier, white is bad and red is bad. We have a lot of this here. And our cluster is basically fully utilized memory-wise, even though our workflow is not even half finished. And this over here is like the new P2P shuffle algorithm that's on by default. Memory usage is very, very low. Everything's blue here. Nothing's really in an area of risk that it will hit some threshold at some point. And there's basically no white here. The workflow I have later is there's barely any white. You have a little bit here, but that's really not a problem at all. So the conclusion of this is the new shuffle algorithm is able to shuffle at constant memory. So there's no huge increase. If your data set is huge, this doesn't matter. You can still process this with like, I don't know, if you have a 10 terabyte data set, you can easily process this with 500 gigabytes of memory if you never have to hold the whole data set in memory. We have run benchmarks of this with like 30 workers to process a 10 terabyte data set. That wouldn't have been possible before that at all. As I said, shuffles data at constant memory. This goes back to the stability thing that distributed Dask users care about. Like we can shuffle at constant memory and we don't strain the scheduler as much. These are huge improvements. Performance is mostly an afterthought in distributed settings. And it's on by default since March. So if you have a new Dask version again, then you will have this by default. You don't have to do anything specifically. I'm currently working on adding logical query planning to Dask. This is the last sub-point of the presentation. Currently, Dask is just doing whatever you want, and it doesn't do anything with your query. So we have a Parquet file here, might have hundreds of columns, and in the end, we care about one value. What Dask will do is will just execute as you give it to it. So we will read all columns, then filter all, aggregate all of them with sum, and then we will select one single value. It's a lot of work for only one number. So what query optimization will do for you is like it will take a look at your query and figure out that this is really not that intelligent what we are doing here. So it will restrict, for example, in read Parquet, the columns to X and ID. So we only read the columns that we actually need. A little bit of a smaller improvement is that we're still summing ID and X, even though we only need X. So what the query optimizer will do in the next step, it will just push the X in front of the sum. Obviously, this has way less impact than the previous modification. But if you have more columns and more complex filters or merges, this is still like relevant performance-wise. And obviously, you can do this by hand. But if you have like thousands of columns and you need like, I don't know, 150 of them, then writing all of them down is not really what you want to do. This is where the actual power of query optimization comes in. Also, if you have very complex queries, the query optimizer will figure out which column selection needs to be in what place and so on. You don't have to think about this manually. It's just another optimized method that reorders the query however it thinks it's best for users. And for the end user, it doesn't really matter. The API will mostly stay the same. It's just under the hood that there's a new layer between the user provides an input query and the Dask scheduler actually starts executing stuff. In between there, we will reorder the query as much as possible, as necessary. Why are we doing this? Like Dask exists for like 9 years now, and we're only starting this now. Historically, Dask focused mostly on the physical scheduler that schedules stuff on the cluster as efficient as possible. It didn't bother much with reordering what the user provided. This is like the huge difference between Spark and Dask. The Spark scheduler isn't that powerful, but they have a very powerful query optimizer. And Dask is exactly the other way around. Like to close the gap from a Dask point of view with Spark, we add this now to Dask so that we have a very powerful scheduler and at least enough query optimization that we can get like 90% of the way there. Benchmarks we've run so far were very promising. Like on larger scale, we already outperform Dask, even though we are not Spark, even though we are not nearly finished yet. We will see how this looks in a couple of weeks. Then we have another demo that I promised earlier. We have like two versions here, the same query that we've seen before. On the left side is the old version. We will give that one a little bit of a head start. And on the right side is the new version with query optimization and P2P shuffle. The first thing that we can see is that our right version is way faster in telling the scheduler what to do, while the left version is still like thinking about what's on the plate now. And like what you can see here, there's barely any white, a little bit of red because we do an aggregation at the end. This is necessary, but that's it. And like our right side is already finished. It was very, very fast. We had a very homogeneous like scheduler view, while the right side, the left side, the old version is still out there like hustling along. We basically can see what we have seen previously, like a lot of white, a lot of red. I just restart this one. While here there is none of this, like no white, everything is busy. We have way less number of tasks, like our biggest number of tasks is 427. This is because we can drop a lot of unnecessary work in this query that we know that we don't actually need. While over here we have 62,000. Like I can probably run this 10 times until the other one is finished for the first time. So everything that's like optimizable is way a lot faster. This is like based on P2P improvements in the shuffle algorithm, but also on the query optimizer that just drops a lot of work that's necessary here that's performed on the left side. So going back to the presentation real quick. I have like a couple final words, basically. What can you do now? Like we've seen a lot of improvements in pandas and Dask. Most of them are already in a state that users can benefit from them if they want. Copy and write can be turned on through setting the copy and write flag to true. I will upload the slides to Discord later so that you can, you don't have to take a photo of the options right now. You can also enable the infer string option with pandas 2.1 or later. This should like reduce your memory footprint by quite a lot and help performance as well, if that's something that you care deeply about and have strings in your workflow. And these are just two options, like two flags to set, and that's it basically. And then for the query optimizer and Dask, everything else is already on by default. You can just install Dask expressions. That's the side project that we're currently working on. We started this week of integrating this into Dask, the main Dask data frame API, but it will still take us a little bit till we can turn this on by default, since the API coverage isn't complete yet. So that's it from my side. Then we can move on to questions.
Awesome. Thank you so much, Patrick, for the wonderful presentation. We have a few questions in the Q&A and also in the chat. The first one, would you comment on copy on write implications beyond eliminating the setting with copy warning? Are there any impacts to method chaining?
No, not to method chaining. Method chaining will work as it did before. It's just that it will be a lot faster, hopefully, depending on what you're chaining. The only thing is chained assignment. That won't work anymore. This is something that is in our copy and write migration docs that are in the pandas docs if you want to read up on this more. But apart from that, if you don't rely on modifying 2 objects at once, you should mostly be good to upgrade.
Next question. Is there a way to review how the optimizer changed the query before it's executed?
By default, no, but you can call optimize by yourself. Just like you would call compute in Dask, and then do a pretty print is the API, is the method that we use for that will print out the query, the optimized query for you. You can also print out the non-optimized query if you want to compare both of them. But if it's a deep query, that's not that helpful because it gets a little bit confusing.
Awesome. Thanks. Would you mind elaborating more on the historical differences of Spark, Dask with respect to polars? How is the scheduler and the query optimizer of polars compared to Dask and Spark?
That's a good question. Dask and Spark are both distributed frameworks that can operate on a single machine. That's debatable by Spark though, or on huge clusters, while Polars only runs on a single machine. So if you have a huge machine and you can process your stuff on that, then Polars is probably a pretty good option. Dask is still faster, in our benchmarks at least, but it's not a huge difference. But as soon as you have to scale out over more than one machine, then Dask or Spark are the only options, because Polars or also DuckDB, they can't do that. Like, they only support executing on a single node. And generally, the Dask scheduler is more powerful than the Polar scheduler, simply because distributed scheduling is a lot harder than scheduling stuff on a single machine. Does this answer the question roughly?
We have time for one more question, perhaps. Are there limitations to Dask expression?
That's a very good question. At the moment, we don't support the whole API yet, but this should change in like the next, let's say in early January, we should be there with full API coverage. And if we're there, like in a couple of weeks, then there won't be any limitations compared to Dask data frames at the moment. We are hoping that the UX is a lot better for users, and that it's also, that it provides obviously a performance improvement, increases stability. But we also are building in a few nice UX features that will hopefully be helpful for Dask users.